In our last two videos, we've been looking at the solution of the damped forced harmonic oscillator equation. We have the second derivative with respect to time plus 2 gamma x prime plus omega naught squared x equals f of t, where f of t is a forcing function, gamma is our damping term, and omega naught is our fundamental harmonic frequency. The solution that we found to this was the superposition of solutions to the homogeneous equation, that is, where f of t equals 0. So we have two such solutions. One is e to the minus gamma t sine of alpha t over alpha, and I put the alpha here for convenience, and the other solution was e to the minus gamma t cos of alpha t over alpha, where alpha is the difference of squares of our harmonic frequency and our damping frequency to the 1/2 power. We found a convolution kernel through Fourier transform and contour integration means that has the form of theta of t times g of t. Happens that it is one of our homogeneous solutions weighted by a Heaviside theta function is in fact our integral kernel, which pulls in all of the contributions from our forcing function if we convolve our integral kernel with f of t. We have informally called g of t minus t prime a Green's function for this equation, but we haven't justified that. And in this video, we're going to justify that. We do that by introducing a linear differential operator for our differential equation. The second derivative with respect to time plus 2 gamma times the first derivative plus omega naught squared. So we can rewrite our differential equation as L of x of t equals f of t. What we want to show is that L, when applied to our convolution kernel, g of t minus t prime, is in fact the delta function t minus t prime. Now we'll go about doing that. What we need to do is we need to take derivatives of our function. So we have g equals theta small g. So our first derivative is theta prime g plus theta g prime. Now theta prime, we formally say that that is the delta function. So delta g plus theta g prime. Our second derivative is delta prime g plus delta g prime plus delta g prime plus theta g double prime. And here I've taken the derivative of theta as delta, so we have delta g prime. We want to group our delta g primes. So we have delta prime g plus 2 delta g prime plus theta g double prime. Now we can write out L, or specifically write it out L of g. So L of g is second derivative plus 2 second derivative term plus 2 gamma times the first derivative plus omega naught squared g. So let's write all of that out. And as we write it out, we're going to group our terms that have theta dependence. So the non-theta dependent terms are delta prime g plus 2 delta g prime plus theta g double prime. So those are 1, 2, 3 of the terms from our second derivative. Now we have plus 2 gamma times the contributions from our first derivative. So that's 2 gamma delta g plus 2 gamma theta g prime and theta g prime. And our last term is the 0th order term is just omega naught squared g. there is our linear differential operator applied to our presumed Green's function. And we have here a theta function, step function times 0, because g of t is also one of the homogeneous equation solutions. So we're left with just LG equals theta prime g plus 2 delta g prime plus 2 gamma delta g. Now we have to make sense of delta prime g. So let's do that. Page. What do we mean by delta prime g? So delta prime g, we give this meaning by applying it to a test function f. And that application is a convolution. So we convolve delta prime t minus t prime times g of t minus t prime times our test function f of t prime, t prime. I want to expand out this term here using the reverse chain rule. So we want to say that that is the derivative of delta of t minus t prime g t minus t prime minus delta of t minus t prime g prime t minus t prime. Reversing the chain rule here, we've essentially done integration by parts. And we're left with derivative of the function with respect to t of delta t minus t prime g of t minus t prime f of t prime t prime minus delta of t minus t prime t prime t minus t prime f t prime t prime. We can now go ahead and evaluate this integral. So delta of t minus t prime is going to pick up only the conjugations where t minus t prime equals 0. So that's g of 0 times f of t. G of 0 times f of t. But g of 0 is 0 because we have a sign. And we're just left with delta prime g equals minus delta g prime. So that is what we mean by, in this particular case, where g of 0 is 0, delta prime g equals minus delta g prime. And look back to where we were before, if LG was delta prime g plus 2 delta g prime plus 2 gamma delta g. And now we can expand out this delta prime plus minus delta g prime plus 2 delta g prime plus 2 gamma delta g. And grouping our terms of delta g primes, we have 1 delta g prime plus 2 gamma delta g. And we've just seen that when we evaluated delta g f of t with the test function f, we got 0 in this particular case. So this term here is 0, and we're left with LG is just delta g prime. So LG equals delta g prime. What we want is LG equals delta. don't quite have that. But so we have to apply the same trick. We want to apply LG to a test function and see what we get. So if we apply LG to a test function f, that means that we have delta t minus t prime, g prime, t minus t prime, f of t prime, dt prime, the entire range. So what is g prime? Just remind ourselves, g equals e to the minus alpha t sine alpha t for alpha. So g prime is minus gamma g plus e to the minus gamma t cos alpha t. So we have here the side of g of f is the interval of delta t minus t prime times g prime, which is minus gamma g t minus t prime f of t prime dt prime plus integral delta t minus t prime e to the minus gamma t minus t prime cosine of alpha t minus t prime f of t prime dt prime. Now we have delta of g, and we've just seen that was going to give us a g of 0, which is 0. So this whole first term is 0. And we're left with the application of LG to F equals e to the minus gamma 0 times cosine alpha 0 times f of t. But e to the minus gamma 0 is 1, and cosine of alpha times 0 is 0. The cosine is 1, and we're left just f of t. So LG applied to a test function f is f of t, which basically means that LG can be LG of t minus t prime equals delta t minus t prime. It's precisely what we set off to show. And you have to be really careful with your factors of 2's and your minuses and pluses, and eventually if you do all the steps right, you can show that you do in fact have a delta function relationship when you apply the linear differential equation operator for our forced damped harmonic equation to our convolution kernel, that it is a Green's function for that particular linear differential operator. That is all for today.